In our final video on acids and bases, we're going to shift gears and focus on Lewis acids and bases. So remember, this is a different perspective compared to Bronsted-Lowry. After a brief introduction, we will introduce some new terms as well. While the Bronsted-Lowry definition focused on the proton, the Lewis definition focuses on electrons. So a Lewis acid is an electron acceptor, and a Lewis base is an electron donor. Now let's look at an example that's actually the same as what we saw with Bronsted-Lowry. So if we have hydrochloric acid and it reacts with ammonia, this can grab a proton. These electrons move on to the chlorine, giving us Cl-, where this is a new lone pair, and NH3, where that nitrogen is also connected to a new hydrogen, so we have NH4 with a positive formal charge. Now, according to the Bronsted-Lowry definition, this is the acid because it donates a proton, and this is the base because this is what grabs the proton. Well, according to the Lewis definition, this is the base because it donates electrons to this other molecule, and this is the acid because it accepts the electrons from the nitrogen. So we can say that HCl is the Lewis acid, or more specifically, the hydrogen is the Lewis acid. So all Bronsted-Lowry acids and bases are also Lewis acids and bases. So why do we bother with the Lewis definition? Well, the Lewis definition goes further. We could, for example, look at a compound called BF3, boron trifluoride. This can react with diethyl ether, and the oxygen can share its electrons with the boron. So this would be a Lewis base because it is an electron donor. This is a Lewis acid because it is an electron acceptor. This forms what's called a Lewis acid-base complex. We have a new covalent bond between the boron and the oxygen. Oxygen still has a lone pair, but it now has a formal charge of +1. Boron has a formal charge of -1. If you're doing synthetic organic chemistry and you need to use BF3, well, you can't just get a bottle of BF3 because it's always in ether, and so you're using BF3 etherate. So notice this would not be a Bronsted-Lowry acid-base reaction because there's no proton transfer. But this is a Lewis acid-base reaction because we have this Lewis base donating electrons to this Lewis acid. When we think about Lewis bases, we can think about all Bronsted-Lowry bases. So we could have an amine, we could have an alcohol or an ether, right? These are all things where we have lone pairs that could be donated to another molecule. We could have something with a carbonyl, a C double bond O, and what's over here could be still a wide variety. So I'm using an R group to stand for basically anything, any carbon chain, just any organic molecule. So if we have a nitrogen, if we have an oxygen, if we have a carbonyl, now this Y group, this could be another carbon, it could be a hydrogen, it could be an oxygen. So there's a wide variety of structures. But basically, everything that we saw as Bronsted-Lowry bases could also be Lewis bases. Now, what about Lewis acids? All Bronsted-Lowry acids are also Lewis acids. So we can have HX, H2SO4, we could have carboxylic acids. All of these are also Lewis acids. But there are some additional acids that are Lewis acids but not Bronsted-Lowry acids. So for example, we can have some cations such as lithium or magnesium. These are commonly used as Lewis acids. And there are some metal compounds such as aluminum trichloride, titanium tetrachloride, and iron trichloride. So these are important Lewis acids that are not Bronsted-Lowry acids. Now, even though the Lewis acid-base definition is broader than the Bronsted-Lowry acid-base definition, usually when we talk about acid-base reactions, we are going to use the Bronsted-Lowry focus. But we use the idea of Lewis acid and Lewis base, but a little bit differently. So let's think about this again. If we have a Lewis base, this is an electron donor. So this is something that might have a negative charge, but it probably has extra electron density, so we can think of it as having negative character. Maybe it has a lone pair, not necessarily, but it is electron rich and it's able to share. So let's think about this as a dating scene, and a Lewis base is somebody who has extra negative character. It wants someone with positive character. So a Lewis base can also be called a nucleophile because it loves a nucleus. Remember, a nucleus has positive charge, so a nucleophile is somebody that wants somebody with positive character. Now, the symbol that I use for a nucleophile is Nu because that's nice shorthand, but I also use the U with an umlaut, so the German U, because this reminds me that we might have a lone pair of electrons that's able to share. It's not a smiley face, but it does look pretty happy. Sometimes nucleophiles can be happy. But this is a symbol that I use for a nucleophile. It doesn't always have a lone pair, but it does have extra electron density that it is willing to share. It is willing to donate its electrons. Now, what about a Lewis acid? So a Lewis acid is an electron acceptor. So it probably has positive character. And so back to the dating scene, because it has positive character, it wants somebody that has negative character. So a Lewis acid is also known as an electrophile because it loves electrons with their negative charge. The symbol that I use for electrophile is an E plus, E for electrophile, and then the plus, this reminds me that it has positive character, that it needs electrons, and so it will accept electrons. So again, not all nucleophiles have lone pairs, not all electrophiles have a positive charge. These are just symbols that can help you to remember the characteristics. So rather than thinking about Lewis acids and bases, we will talk very, very frequently about nucleophiles sharing electrons with electrophiles. Now, if you understand Bronsted-Lowry acids and bases in terms of proton transfer, and if you can understand nucleophiles reacting with electrophiles, then you understand about 95% of the organic chemistry that we're going to cover this entire year. So that means you're in good shape. It also means that it is worth putting in the time and effort to get a solid understanding of Bronsted-Lowry acids and bases, as well as Lewis acids and bases as electrophiles and nucleophiles. So get lots of practice, take your time, and make sure you understand these.